Hello everyone. I'd like to go over some math background to get us to understand variational autoencoders from first principles. And so first thing I have to talk about is entropy, which I know I've mentioned before, but I want to go into it in a little bit more detail just so we're really clear on it. So entropy is something we use. It's a measure of the average information content of a random variable. And more precisely, it is a measure of the average number of bits you would need to use in an optimal representation of a random variable. And so the precise definition is, we denote it by h. H of some random variable x is the sum over all possible values that that random variable can take on. So I'll say sum over I of the probability that x equals that value, or maybe I'll denote it as xi. That's the ith value the random variable could take on. That probability times the log base 2 of 1 over that probability. Okay, so there's the definition. And so what it is, you look at it and you say, okay, there's different values that my random variable can take on. So as an example, let's consider a fair coin. So a fair coin, we'll say, xi could be, we'll say x is in 0, 1. So maybe it's a 0 if it's a tails, 1 if it's a heads. And so for a fair coin, we have the probability that x equals 0 being 0.5, and then the probability that x equals 1 also being 0.5. And so this term here is the probability of my random variable taking on a particular value. This term here is the number of bits that I would need to use to represent that. So in this example, I look at this and I say, okay, the probability of each of these is 0.5. And then that would be times log base 2 of 1 over 0.5. So that would be it for tails. And then plus, because I'm summing up over all possible values, 0.5 chance of being heads times log base 2 of 1 over 0.5. Which, when you look at that, that's saying, okay, half of the time I'm going to be a tails, and how many bits am I going to use to represent that? Well, it's log base 2 of 1 over the probability, which in this case is log base 2 of 2, which is 1, times a half, plus 1 times a half equals 1. And so what this tells us is for a fair coin, we need to use 1 bit to represent the outcome. Which makes sense, we use 1 bit of information. It's a 0 if it's a heads, or 1 if it's I guess 0 if it's a tails, 1 if it's a heads. But it changes a little bit if it's not a fair coin. Because what I could do is say, let's say that maybe P is the probability of being a head. So we'll say P is probability of being a head. Or maybe I'll call it PH for probability of being a head. And then so probability of being a tails is 1 minus that. And so if I apply this formula over all the different possible values here, I'll get that my entropy is equal to probability of heads times log 2 of 1 over probability of heads plus the probability of tails times log 2 of 1 over probability of tails. And if I plot this as a function of the probability of being a heads, I get this interesting shape here. So I see when it's a fair coin, when it's a half probability of being heads, so let me put the X label there. When it's a fair coin and it's a half probability of being heads, we have an entropy of 1. But actually the entropy goes down if it's an unfair coin. So if we either have a larger probability of being a heads or a smaller probability of being a heads. And the idea is that on average, a coin flip doesn't give us as much information if it's not fair. Because we expect it to be a certain value more often than not. And so what happens is the amount of bits that we need to use to represent, let's say the heads was a probability of 0.8 here. Well, the amount of bits that I would need to represent that would be log 2 of 1 over 0.8. which is only about a third of a bit. So I only need a third of a bit of information to represent an unfair head. In other words, it just doesn't give me that much information. I see it's a head. Yeah, I thought it was going to be a head. When I get a tails, though, I get more information. So when I get a tails, I actually need more than 1 bit to represent that. I'm pretty surprised to have gotten a tail. But that doesn't happen that often, so it's actually weighted down by the probability 0.2 there. So anyway, again, this is just, it's a weighted average, actually, of the number of bits that you need to represent each value of the random variable. Now, for a slightly more interesting example where there's more than just 2 possible values of the random variable, we can consider representing the characters of text. And so this was an assignment I actually gave in my 174 class, those of you who had it, on building Huffman trees. And I showed you how there was a snapshot of the internet from Google from the 2000s. And here's a histogram of how often each character in the alphabet is used, plus a space, plus a period. Now, that's 28 total characters. If I was just going to use the same number of bits to represent each character, I would have to use 6 bits. That's actually enough for me to represent 32 possible values, but that's the nearest power of 2 above 28 that I could choose. Would be with 5 bits there, 5 bits. So yeah, 2 to the 5th is 32. So anyway, but actually, it's a little bit wasteful because we don't actually fill up all the 32 bits. And the other thing is certain characters occur more often than not. So, as an A, for example, I probably can get away with representing an A with fewer bits than I would by representing a Q, for example. And so I don't necessarily have to use the same number of bits for each character. What I'll do is I'll try to use fewer bits for characters that occur more often, and more bits for characters that occur less often, and then I'll reach my entropy. So this is kind of a lower bound in the amount of bits that you need to store something. So just to show you, I've computed this ahead of time. Well, I didn't compute it ahead of time. I stored this information ahead of time with these counts, and all I did was I just normalized them so they sum to 1, so that they're actual probabilities. So I divided the counts of A by the sum of the total counts of everything else. I divided the counts of B over that same sum. And so that's what this code does. So I see that, interpreting this as a frequentist probability, the probability of seeing an A, knowing nothing else, the probability that I just pick a random character out of the internet, is about 0.07, which is significantly higher than a probability of picking a Q if I pick a random character out of the internet, because the probability of picking a Q is only about 0.001. And so just to show you how many bits I would need for each character, so if I went through here, I said for C and probs, and I print out that character, and then I print out log 2 of 1 over the probability of that character. So I see, okay, A needs about 4 bits, B needs 6 bits, and I see down here like a Q needs almost 10 bits, a Z needs almost 10 bits, right? So hopefully that matches our intuition there. We're trying to compress this, so we're going to try to use fewer bits to represent the characters that occur more often. So if I want to compute the entropy here, I'll say, well, that is the sum of the probabilities. So I'll just say here probs.values. Actually, let me just compute that ahead of time here. Say P here. It's just when I'm computing the entropy, I don't care so much what the particular values are. I just care what the probabilities are. So I'll say, let me just put this in a list here, list of all my probabilities. And so that would be the sum of the probabilities times log base 2 of 1 over those probabilities. And turns out it appears, oh, whoops, okay. I meant to say log 2. Okay, so we were using 5 bits, but apparently we can get away with about 4.3 on average in an optimal representation. Now, in this lab in my 174 class, I showed how actually you can build something called a Huffman tree, where you create a leaf node for each character that you're trying to encode, and you merge the leaf nodes of the least frequently occurring things first, and then eventually you end up at a rooted tree. And in this tree, you can walk from the top down and figure out the binary representation of each character. So an E here would be 0, 0, 0. So I'm not going to go into detail on the Huffman tree here. I'll leave that in a link if you want to So I just stored this ahead of time, the codes that I learned in this Huffman tree. And so you can see, for example, an A required 4 bits, but a Z actually required 10 bits. And so let's look at the average number of bits. So I'll do a weighted sum according to the probability. So I'll say, all right, let's figure out if I go through each of these characters and I say, okay, average bits plus equals the probability that that character occurred times the length of what the Huffman coding was. And what I get is 4.328, which is darn close to my 4.31 lower bound from entropy. So it turns out these Huffman trees are pretty cool. They're nice ways to construct what are called prefix-free encodings of my characters that get close to matching the entropy. So it's better if I use these codes on average. I'm going to save myself space because I'm closer to the actual information capacity here. So using 4.33 bits on average is going to save me space, compress me a little bit over using the 5 bits, which was in my naive code here, where they each had the same length. So that's what entropy is. And actually, let me take this formula and I want to rewrite it a little bit by noticing that. So first of all, this log of 1 over the probability, I think it's a little bit clearer to see there why this would be bits when it's written that way, because the less probable you are, the larger the argument to the log gets, and so the more the log grows. And you know, when I do log base 2, it's always going to give me the number of bits that I need to represent something. But often what you'll see is people will use the rule of logs to take this out to its reciprocal. So I'd actually write it like this. So it's actually the negative weighted sum according to probabilities of just the log. Looks a little bit nice, so you don't have that quotient. The other thing I want to note here is if we go back to looking at Gaussians, for example, this is not a discrete random variable anymore. This is a random variable that can take on any float, any real number. And so it uses something called a probability density function instead to represent it. In that case, we don't have a sum because we don't have a finite number of possible values. But we have the infinite analog of a sum, which is an integral. So what I would do is just integrate over all x, the probability that x, the probability density of x times log base 2 of the probability density of x. And so here's the continuous definition of entropy here. Whoops, forgot my negative sign. But actually, both of these are an example of what's known as the expected value of a random variable, which is the weighted sum of the random variable weighted by its probabilities. So I look at this and I see, okay, actually what the entropy is, it's the negative weighted sum of the log base 2 of a probability of the random variable times the probabilities as the weights. So you'll often see, and I'll use this notation moving forward because it's just a little bit less cumbersome to work with. H of x is defined then as the negative expectation of log base 2 of the probability of x. So, and I'll say E over P. So denoting that P is the probability distribution. So this is maybe a more common way of seeing it written. And actually, one more thing I'll do. This is if you wanted the average number of bits. Turns out, actually, often people use the natural log. Can use the natural log instead to get average nats. That's the unit of information. That's what it's called. So this is the definition that I'll stick with moving forward because that's what you usually see. So natural log. So the weighted average of the natural log of the probability over all possible values of my random variable. So now this notation doesn't matter whether my random variable is distributed as a continuous variable or as a discrete variable. I can always unify the notation like this. Okay, now I have the definitions in hand to define something called cross-entropy, which is a measure between two distributions. So the cross-entropy between a variable distributed as Q, so probability distribution Q, with respect to the probability distribution P is defined as, let me define it first actually using discrete random variables just so it's really clear what's happening here. So I would say HPQ is equal to negative sum over all the possible variables values I of Pi. So we're going to use the probabilities from P, but then we're going to take the log of the probabilities in Q. So that is the definition of cross-entropy in the discrete case, and we would write it in general as HPQ is the negative expectation, according to P, of the natural log of Q. And so I look at this formula, I say, it's as if you thought you were using the distribution from Q. It's like, okay, I set up my bits according to Q. Here maybe was the Q that I came up with, the probabilities according to these counts. But then maybe in real life, they were actually evenly distributed. So I'm going to use just even probabilities there. That's one example. Actually, let's do that example. So if I had P being these probabilities here, the ones that I got from the counts. So I'll say P is equal to probs. And then I'll make Q, or actually I guess I'll say Q is equal to the probs. That's what I was using. But then P I'll make be just 1 over the length of probs. So printing out Q, actually I'll say np.array list probs.values. So that's what Q is. And so, they're not all the same, but I'll make them the same in P. And so if I compute the cross-entropy here, it's going to be negative sum of P times log. And let me use log base 2 so I can compare it for a second. Log of Q. So this is saying, hey, if you were wrong about the distributions of the characters, and you thought that they occurred in this skewed manner like this, but in reality they actually occurred evenly. So I'm going to use my P as just totally even, or uniform distribution. You're actually going to end up using 5.5 bits on average. So one thing you notice about this, 5.5 or 5.6 bits is greater than 4.3 that we got from the entropy. So one thing that you can always say is that, and you can prove this using Lagrange multipliers. So one can prove, for example, using Lagrange multipliers, if you ever heard of that. but hopefully it's intuitive here. It's like you were wrong about what you thought the counts were. So what you can prove is that HPQ is greater than or equal to H of P. So the entropy of a random variable is always less than or equal to the cross entropy of another random variable with respect to that random variable. Okay. Another thing we can notice is that these the cross entropy is not symmetric. So just a quick note here. Cross entropy is not symmetric. So what it means is if I switch the role of P and Q, I don't get the same thing. So I should say not necessarily symmetric. So what that means is that HPQ does not necessarily equal to HQP in general. So using, the distribution of P with the correct distribution of Q is not the same as using the distribution Q with the correct distribution of P. So yeah, if I were to change the roles here of Q and P, I would get something different. I would actually get 4.8. Okay, so given that the cross entropy is always greater than or equal to the entropy, we can define a quantity which is the difference between the two, and we call this the Kullback-Liebler divergence. So KLPQ is going to be equal to cross entropy PQ minus entropy of P. And so if I go ahead and plug in, let me just work with the discrete variable to get a handle on this to begin with. If I plug in this equation, then what I'll see is, so KLPQ is it's the cross entropy, then minus the entropy. So I'll just put them together under the sum here. So entropy would be pi natural log of pi. So if I plug and chug this stuff in here, what I get is that. And I can actually simplify that a little bit. I'm going to use a couple rules of logs here. The log of a quantity minus the log of the other quantity is the log of the quotient of the first one over the second one. So I can actually write this as, and they have the same coefficient there, so I'll just, do the distributive property, take the pi out, and then it's going to be natural log of qi over pi. So I can write it like that. And actually, at this point, people often get rid of the negative sign as well. So if you put a negative sign through a log, it flips the quotient around. So you can actually write this as positive pi over qi. All right, so I could write this, if I wanted to use expected value for a general random variable, I would say this is the expected value according to p of the natural log of p over q. All right, so that's what the Kullback-Liebler divergence is equal to. And so it's a measure of how different two different random variables are. And the reason I went through all this pain is exactly to get to this point, because now we have a measurement of how different two different random variables are. And actually, I mean, yes, the cross-entropy gave that as well, but in this case, the KL is actually equal to 0 if they're the same. So note that KLPQ is equal to 0 if and only if P and Q are the same distribution. So what we'll do, so we can use this as a loss function. So something that we'll try to minimize, and that should be equal to 0 when the distribution of a variable that we're learning is exactly equal to a target distribution. And so if you recall, when we were coming up with variational autoencoder, we had some kind of penalty to say, well, how similar is the distribution of your z given x to the prior x. And so we'll measure that using the KL divergence. So that's it for the math background, and what I'll do is I'll now apply this KL divergence and derive the rules for variational autoencoders. Now we have everything we need, and I can go ahead and finish that.